welcome to another module in this massive open online course. So we are looking at the average code length, and we have seen a very important result wherein the average code length is bounded by the entropy of the source, and more importantly, to achieve this lowest possible average code length, one has to encode symbols such that the length is given by log to the base 2 1 over pi, where pi denotes the probability of the ith symbol. Okay. Now let us look into this further. So we would like to look further into this average code length, how to achieve or how to progressively decrease that is what we want to know, how to achieve progressively lower code lengths. What we would like to do is we would like to design a mechanism whereby we can progressively keep lowering the code lengths, moving towards the lowest possible average code length, that is of course given by the entropy of the source. Okay. Now for that, what we have seen in the previous module, recall, optimal code word length, not code length, optimal code word for symbol I or for symbol SI. Remember, we had derived this from the constraint optimization framework, that is Li equals to log to the base 2 1 over pi. This is the optimal code word length. Okay. Now obviously, now you will observe that this need not be an integer, that is the problem. So this need not be an integer, which means that of course when you are using binary information bits, for instance, to represent each symbol, then we can only use an integer number of bits. I cannot use half a bit, alright. So I can only represent each symbol using an integer number of bits. Okay. So therefore I cannot, if this quantity log to the base 2 1 over pi is not an integer, then I cannot choose that many bits, alright. So naturally the recourse is to choose the integer which is closest to it. Now obviously I cannot choose an integer which is lower than this. For instance, if this is 4.5, I cannot choose 4, because then the average code length would become lower than the intro. It would violate the constraint. Okay. But I can always choose an integer which is greater than this. So I can choose the integer which is the next highest integer corresponding to this, which is given by the ceiling function of this. Okay. So I can choose Li equals the ceiling function, because if you choose the lower integer, then you can violate, because you cannot decrease. We have a lower bound, I cannot decrease it beyond that, is I cannot make it in the lower bound, but I can always choose an average length, or I can always choose a length which is higher. Okay. So this is, remember, this is the integer ceiling function. This is the integer ceiling function, correct? Gives the next highest integer. Example, for example, ceiling of 4.7 is equal to 5, etc. So on. It is a very simple function, all right. It's you take the next highest integer, because it is not an integer, you approximate it by the next highest integer. Okay. So therefore, what I have is basically, now if you look at this log 2 to the base 1 over pi, which is your Li, which you are setting your Li, it naturally follows that this is less than or equal to log 2 to the base 1 over pi plus 1 and log to the base 2 1 over pi, and that can be easily seen. For example, ceiling of 4.7 is 5 and this is less than or equal to 5 plus 4.7 plus 1, this is less than or equal to 4.7 plus 1 equals 5.7, and this is greater than or equal to 4 and this is greater than or equal to, I am sorry, 4.7. Okay, this is greater than. So we have the inequality that x is less than or equal to ceiling of x less than or equal to x plus 1. Naturally, because the ceiling of x is the next highest integer, so it is greater than or equal to x, and the next highest integer lies within within a distance of 1 from the given quantity. So it is obviously less than or equal to x, by ceiling of x is less than or equal to x plus 1. Okay. Now using this, now if I multiply on all the three quantities by pi and take the sum, so I will have pi log to the base 2 1 over pi summation of I equal to 0 to m minus 1 less than or equal to summation I equal to 0 to m minus 1 pi log to the base 2 1 over pi ceiling, which is nothing but Li, and in fact if you look at this quantity summation I equal to 0 to m minus 1 pi Li, this is L bar, which is less than or equal to summation I equal to 0 to m minus 1 pi log to the base 2 1 over pi plus 1. Now obviously if you look at this quantity is nothing but the entropy, and this quantity can be simplified as follows. This quantity is, if you look at this, if you take out the bracket, remove the brackets and expand, this is summation I equal to 0 to m minus 1 pi to the base log to the base 2 1 over pi plus summation I equal to 0 to m minus 1 pi. Now this quantity is once again h of x, and this quantity summation pi, summation of all the probabilities, that is total probability, which is equal to 1. So this is basically hx plus 1, and therefore what you derive net inequality we obtain, what we obtain is basically we obtain the inequalities hx less than or equal to L bar less than or equal to hx plus 1, and this is interesting because it shows that you can obtain using these lengths, that is approximating by integers, you can obtain a code which is within 1 bit of the entropy. So the lower bound is entropy, ideally we would like to achieve that, but observe that the interesting thing about this theorem is basically is source coding theorem, which we derived from the Kraft inequality. is it only gives us a lower bound, that is it tells us that the average code length is greater than or equal to the entropy. However, it does not tell us how to build a code with this minimum average code length, that is a code length achieving entropy. Alright, so we have to devise mechanisms. So one simple mechanism is to choose the code lengths to be the ceiling of log to the base 2 1 over pi, where pi is the probability of the ith symbol. And we have shown that such a code is within 1 bit. Such a code is within 1 bit. It lies between these bounds hx and hx plus 1. Is within one bit of entropy. What we mean by that is that lowest is hx, so it lies between hx and hx plus 1. So at most it lies at hx plus 1, which is within 1 bit of the lowest possible, that is 1 bit of the entropy. Okay, so that is the point. Okay, so thus there exists a code which is within 1 bit, average bit, that is whose average length, code length, is within 1 bit of the source entropy. Now, using this principle, how to achieve a code length, if you are not arbitrarily close to the entropy. Now for that, what we can do is, let us say, consider now a sequence. Now how to achieve that? Consider the sequence x1, x2 up to xn. Now that is, we are looking at n symbols together. Or a group of n symbols, and let us denote by the vector x bar. Now let us say I encode this vector or encode the block of, so let us say I encode this block, rather than encoding a single symbol, let us say I encode in blocks. Instead of encoding a single symbol, let us say I encode blocks or groups of symbols. So n symbols together comprises of a block. Okay, n IID symbols, remember, because we are considering a discrete memoryless source. Okay, so these symbols are from a which implies that the symbols are independent, identically distributed. Now, therefore, if symbols are independent, identically distributed, let the average code length of this be L bar n. So we encode blocks that is when encoding blocks of size n. The average code length is L bar of n. Now, we know that Hx bar equals entropy of this block source right. If we consider a new source which is generating this block of n symbols together, if I consider that as a new source. So, what I am doing is basically I am taking this source, I have my source which is generating symbols x1, x2, xn, I am forming a vector and considering this block, okay. And now this is basically your vector x bar equals vector. So, considering this as a block source. Now, the entropy of this block source, discrete memory less source, since the symbols are IID, you can easily see that h of x bar is n times h of x, and this is a very important result. That is, if you look at the entropy of this block source, the resulting entropy is n times the entropy of the original source, and the reason is very simple, because the symbols are IID, correct. So, you can look at it multiple ways. When you consider n symbols, the information in n symbols is n times the average information in n symbols, since the symbols are independent, is n times the information in a single symbol, alright, makes sense, right. So, the average information in a block of n symbols is n times, correct, n times the information, average information in a single symbol, since the symbols are independent, okay. And this can be rigorously proved also, and I will illustrate how. This is intuitive. Equals n times average information in a single symbol, okay. So, average information in a block of n symbols equals n times average information in a single symbol. And you can also see mathematically, theoretically, in theory, if you have a symbol x1, x2, or if you have a symbol with x1 equals s1, x2 equals s2, or let us say x1 equals and x1 equals, for instance, let us put it this way, because x1 need not equal to s2, x1 equals si1, x2 equals si2, so on, xn equals sin, then the probability is simply the multiplication pi1, pi2, pin. So, the probability is simply the multiplication, correct. And therefore, in the log domain, when you multiply the probabilities in the log domain, when you take the log that you do in the entropy, when you take the log, then you get the addition of the log probabilities, alright. So, this converts to an addition in the logarithm, that is, once you take the logarithm, these you consider you get the addition in the log domain, okay. So, you can see the information is naturally proportional to the logarithm, so the information adds up, okay. So, that is the information. So, the hx bar, and once you can again see the key assumption here is the independence, okay. The key assumption independence, or IID rather, IID arising from the discrete memoryless source. Okay, so that has to be kept in mind. Now, therefore, if the average, now from the previous result that we have derived for the source, that is also applicable to this block source, right. Therefore, what we will have is this L bar n, that is this length L bar n, average code length for this block source comprising of n symbols is less than or equal to hx bar plus 1 is less than or equal to hx bar, okay, is less than or equal to hx bar, okay. And now we know that hx bar is n times hx, so replacing hx bar by n times hx, I have this is less than or equal to n times hx plus 1, this is less than or equal to n times hx plus 1, this is less than or equal to n times hx. Now, dividing throughout by n, we get L bar n by n is less than or equal to hx plus 1 by n is greater than or equal to hx, okay. And therefore, now look at this quantity L bar divided by n, this is code for block of n symbols divided by n. You can think of this as average code length for a single symbol, average, this is code, that is what you can think of this as basically, let me just write in this is the number of bits for n symbols divided by n, okay. So, if you look at this, because the block comprises number of bits for n symbols divided by n equals so this equals average number of bits. So, it is a number of, so you are looking at a block of n symbols, right, you are looking at the average number of bits per n symbols divided by n. So, this is the average number of bits per a single symbol, okay. And now you observe this is within hx plus 1 over n, okay, within 1 over n, this is within 1 over n bits of entropy. And therefore, now by increasing the block length n, I can make it arbitrarily closer to entropy. So, for instance, if n equal to 10, then becomes 1 over 10, that is within 0.1 bits of entropy. If I make n equals 100, that is if I encode blocks of 100 symbols, it becomes 1 over 100, that is 0.01. So, it is between hx and hx plus 0.01. So, it is within 0.01 bits of entropy. So, therefore, by increasing n, that is by coding across larger and larger blocks, I can make it arbitrarily close to the entropy, that is the point. So, by coding, by increasing n, one can make it arbitrarily, one can make the average code length Okay, let's rather than saying it, one can make average code length, one can make the that is within 1 by n bits, and you can see that limit n tends to infinity, 1 by n tends to 0, which implies that the gap between Hx approaches 0 for large and larger block. That is, this is the key. By increasing n means coding over larger and larger blocks. By coding over larger and larger blocks, one can basically approach entropy, one can approach arbitrarily close to the entropy, that is within 1 by n, where n is the block length. Okay, so that is basically the overall scheme one can use to design very efficient, one can use to design progressively, that is by increasing the block length, one can progressively design more and more efficient codes which are arbitrarily close to the lowest possible average length, that is the entropy of the source. Right. So with this we will stop this module, and in the next module we will look at practical schemes for such code construction. Alright, thank you very much.